Yeah. Yes, I agree. Yeah.
All right, guys. So I would like to go through with you and do stoichiometry. So everything, like I said, that we have done really the past couple of weeks, we've just been doing kind of baby steps. We've done grams to moles, we've done moles back to grams, we've done atoms and molecules. So we're going to take all of what we know and we're just going to build on that. So stoichiometry is just going to be one extra step towards conversions. And so make sure you have your periodic table in front of you. Now, the paper that I just passed out to you, that's, we're going to get to that. I was going to actually pass out the slides on the notes, but there's 20 slides and it felt like a lot, and I'm not going to go through all of it today. So I just follow along with me on the notes. So just kind of put that paper, if you want to flip it over actually and take some notes, you can. It's blank. You don't have to, but that felt like kind of the easiest way to go about doing this. So this is on Canvas. If you want to at some point click on it and kind of follow, you can. So stoichiometry. Stoichiometry essentially is all about mole relationships. Okay, so up to this point, we've just dabbled a little bit with moles, and we're going to just take it a little bit further. Okay, so mole relationships, okay, are exactly that. They're relationships between all the different compounds or molecules in a balanced equation. Okay, so look on the board for a second. So when iron reacts with sulfur, the product is iron 3 sulfide. So there is your balanced equation. What it's looking at is 2 moles of iron plus 3 moles of sulfur gives you 1 mole of iron 3 sulfide. So when you look at a balanced equation, so I guess at this point, always double check that an equation is balanced. That's always been a thing, but now especially because you're going to start using the coefficients to be able to convert with mole ratios. And if it's not balanced, it's going to be incorrect. So always double check that your mole ratios or that your equation's balanced so that your mole ratios are correct. Okay, so here's my mole ratio. Essentially, it's a 2 to 3 ratio when I'm looking at iron and sulfur. So I have 2 moles and 3 moles, and it gives me 1 mole of iron 3 sulfide. That is my product. Okay, so a mole ratio compares 2 things at a time. Okay, and it uses the big number, the coefficient out front, to explain how many moles of that item, whatever, it's either an element or a compound or a molecule, and it's going to tell you kind of in a balanced equation how all that works together. So you can write a lot of different mole ratios based off of this equation. You can actually write 6 mole ratios off of this equation, okay? I can compare iron and sulfur. I can compare sulfur and iron 3 sulfide. I can compare iron and iron 3 sulfide. So it doesn't matter which 2 you choose, but you're always going to compare 2 at a time. So let me show you what those ratios are. Okay, so you can write, these are called mole ratios. Okay, and so if I'm going to compare iron and sulfur, okay, both of those are my reactants. If I compared those 2, I can always have 2 ratios out of that. One time iron is on top, so 2 moles of iron over 3 moles of sulfur. Or on the flip side of that, I can have sulfur on top, 3 moles of sulfur and 2 moles of iron. So whatever 2 you're comparing, you'll get 2 ratios out of that. They're just kind of the inverse of each other. And the one that you choose when you're going to start converting will make a little bit more sense once we use this in an actual problem. But in the first case, 2 moles of iron over 3 moles of sulfur, you would use that if you were starting in moles of sulfur. Okay, and if you were using moles of iron, then you would use the second one. And I'll explain what that looks like in a second. Okay, so that's if you're comparing iron and sulfur, and that 2 and 3 is coming straight from your balanced equation. That's why it's really important that your equations are always balanced, and not only balanced, but balanced correctly. So if I wanted to compare iron and iron 3 sulfide, okay, again, you can compare 2 reactants, 2 products, a reactant and a product. It doesn't matter which 2 you compare. Whatever 2 your little heart desires are the ones it asks about, those are the 2 you're going to compare. So if I wanted to compare iron and iron 3 sulfide, again, I can get 2 mole ratios out of that. I can have iron on top and iron 3 sulfide on the bottom, and that's a 2 to 1 ratio. Or the flip of that is 1 mole iron 3 sulfide and 2 moles of iron. And again, those numbers 2 and 1 are coming right from your balanced equation. Okay, and then the last one, 3 moles of sulfur and then 1 mole of iron 3 sulfide, and then the flip of that. So because there's a total of 3 different things in our equation here, reactants and products, I can get 6 total mole ratios. So the mole ratios are really important when it comes to being able to convert. Okay, so what stoichiometry does for us is in the past week or so, you guys have done moles and grams and grams and moles and atoms. But guys, you're always staying within the same molecule or the same compound. Okay, so like last week, if I said I want you to go from grams of water to moles of water, you would be easily able to do that based on the mass, the molar mass of water, and you would convert that because you were just going from grams to moles in the same compound. Guys, what stoichiometry does is I could say if I have X number of moles of water and I want to know, well, how many moles of hydrogen is that? Okay. This is what stoichiometry is going to allow us to do. It allows us to go from moles of one to something completely different. Okay? Last week we stuck with the same thing. Everything that we converted was always the same molecule or same compound all the way through. Now we're going to look at mole ratios and how they allow us to look at one and go to something completely different. Okay? So that's what this next slide is going to show us here. So it says, in the reaction of iron and sulfur, how many moles of sulfur are needed to react with 6 moles of iron? Okay, so now these are easy numbers to deal with, so you could actually probably do this in your head. If you're looking at iron and sulfur here, it's a 2 to 3 ratio. So let's kind of break this down. You'll always be given 2 parts of a problem. You're going to be given what your starting point is. It's called your given, and then it's going to ask you to find something, which is going to be your needed. So I've got a given and I've got a needed. In this case, the problem is giving me moles of iron. How many moles of iron is it giving me? What does the problem say? Yep, 6 moles of iron. So I have 6 moles of iron, and it's asking me to find what?
Moles of sulfur.
Good. Moles of sulfur. That's how I do it. Moles of sulfur. Mm-hmm. So you guys are going to be able to use your mole ratios to convert from moles of iron to moles of sulfur. So this is how this works. You're always going to start with what you've been given. So 6 moles of iron is your starting point. Use your T-chart here, and please write your units, write your units, write your units. It's really easy when you're doing all these conversions to flip-flop and get things confused. But if you write your units and what element or compound it's referring to, it will make your life much easier. Okay, so if you're going to start off in 6 moles of iron, what's going to go down on the bottom of your T-chart here? Okay, moles of iron, because whatever is here needs to cancel out. Okay, right? So moles of iron is going to go on the bottom, and then moles of sulfur is what you're converting to is on top. So this should look familiar because we just saw this mole ratio. Okay, if we're comparing sulfur and iron, we did this already, right? So this is where your mole ratio comes into play. What's the number in front of sulfur? 3. So you write 3 here. What's the number in front of iron? 2. Okay? So you guys are using that mole ratio, sometimes it's called the mole factor, in order to convert from moles of iron to moles of sulfur. Okay, so again, this is kind of your plan here. That 2 to 3 ratio is being used in your T-chart in order to convert. So here, this is how this works. Okay, again, here's your ratios. You already wrote those down. We're choosing the one that has 3 on top, okay, because we're starting in iron. So whatever iron, it needs to go on the bottom in order for that to cancel. So that's why we're specifically choosing this ratio, okay, because of where we're starting and where we're ending. So again, this is what this looks like. This is just your T-chart, okay? You have 6 times 3. You're going to multiply everything across the top is 18, and divide that by 2 is going to give you 9. Okay, so 9 moles of sulfur. And again, this is why writing all your units and making sure that all of those cancel. It was hard for me to do the T-chart on here years ago, so I just set it up like this, but this is just a T-chart, okay? Some people like this way, the way it looks better anyway, so it's up to you how you want to do it. Okay, so you used your mole ratio to get out of one thing into something completely different, and you used your equation to do it. How do you feel about that? That's stoichiometry. Look at you all stoichiometrying it up. That's all that is, right? You guys are always so nervous about stoichiometry. This is it. It won't get any harder. I'm going to add this to what you already know. So it's not going to get harder. But there's going to be more steps eventually, okay? All right. So let's look at this one again. You might not always need to do the full-on setup. I'm still going to set it up for you just to show you. But these numbers are pretty easy. If you look, you have here 1 mole of nitrogen plus 3 moles of hydrogen gives you 2 moles of NH3. What is NH3? Good, ammonia. So if it asks me in the problem, I'm going to compare hydrogen and nitrogen. So guys, whenever you're given an equation, it could have multiple reactants, multiple products, but the question will only ever ask you about 2 at a time. So in this case, it's asking me about nitrogen and hydrogen. That means ammonia is completely off my radar. I don't even care about it right now. So you don't even have to do the setup. I'll show you anyway, but you could easily do this in your head because what's the ratio between nitrogen and hydrogen? 1 to 3, right? So if you have 1 mole of nitrogen, how many moles of hydrogen do you have? 3. Okay, so you just did the setup just in your head because those numbers are pretty easy to work with. So again, not everything will be that simple as far as your numbers and your starting and your ending points go, but that's what you're doing. You're just using the ratios to determine if I have X number of this one, how many will I have of this one? It just allows you to go from one thing to something completely different. Okay. Let's do one that's maybe slightly more challenging. Okay, so now it's going to ask me about nitrogen and ammonia. So in this case now, hydrogen's not being asked about, so it's completely off my radar. So how many moles of nitrogen reacted if 0.6 mole of NH3 is produced? So again, kind of look at this as what are you given? What do you need to find? So what are you given in this problem here?
0.6 moles of.
Yep, 0.6 moles of NH3. And then what's it asking me to find? Yeah, moles of N2. So it's asking me if I am only producing 0.6 moles of ammonia, how many moles of N2 must I have reacted? Okay, so again, always start with what you've been given. I have 0.6 moles of NH3. I'm going to do my T-chart here. Okay, so what's going to go on the bottom of my T-chart? Just give me my my units first. And again, I always recommend start with your units first, then go back in and fill your numbers in. It just kind of makes it easier to figure out. So moles of ammonia is going to go on the bottom, and then moles of nitrogen is going to go on top. Remember with the T-chart, whatever you're converting to always goes on top. Whatever you're converting from is going to go on the bottom. And so we know that moles of NH3 is going to have to cancel. So now I'm to my mole ratio. Where does my mole ratio come from? Where do the numbers go for my mole ratio? The equation, the balanced equation, right? So what's the number in front of N2? 1. What's the number in front of NH3? 2. Okay. What's 0.6 times 1? 0.6 divided by 2. 0.3. Yep, 0.3. Which, if you look at your balanced equation, it's a 1 to 2 ratio. That means that ammonia is literally double whatever your nitrogen was. So 0.6 is double nitrogen, then that would make sense that nitrogen's 0.3. Okay, ratios. So those numbers will always come from your balanced equation. Okay, still feeling okay? Okay. We're not going to get too much in it today, but I've only been sticking with moles to moles. What would happen if I said, you know what, I'm going to use the same problem. I don't want moles of nitrogen, I want grams. Not exception, I'm just adding it to what you already know. Okay, so a mole to mole ratio is just a one-step thing, okay? But because you know how to convert grams and moles, you could easily say, well, I don't want to know moles, I want to know grams. So in that case, you would just continue on with your T-chart. So here, I used my mole ratio, okay, in my T-chart to convert between ammonia and nitrogen. Now that I'm fully in nitrogen, now you're going to do what you guys did last week. You have moles of nitrogen, convert that to grams of nitrogen. Okay, so this is just adding on a step before your moles to grams conversion. So moles of nitrogen, when you continue this, what's going to go down here on the bottom? Moles of nitrogen, remember whatever is on the bottom has to be the same so that those cancel. And then what am I converting to? Yeah, grams of nitrogen. All right, so in this case, when you're converting moles in grams, what number always goes with mole? 1. And what is the mass of N2? 28. Okay, so all I did, guys, was use my mole ratio to get myself into moles of nitrogen. And then I just continued with what I knew last week where I'm going to convert moles to grams. So you would do 0.6 times 28 divided by 2. It gives you 8.4. So 8.4 grams of nitrogen would be your final answer if I asked you to convert to grams. Okay, so again, last week you stuck with the same compound from beginning to end. Stoichiometry is going to allow you to start at something completely different. Then it's going to allow you to convert to something else, and then you can continue on with your moles and grams conversion. So what happens, I'm not going to do this, but what happens if I didn't give you moles of NH3? What happens if I gave you grams of NH3? You would convert to moles first. Then you would do your mole ratio. Then you would do back to grams. So again, I want you to kind of understand here. So if I'm sticking with this example, if I would have given you grams to start with, okay? Grams of NH3, you would have converted to what? What's the next thing that what's the only thing you can convert to in grams? Moles of NH3. So this is what the step that you did last week. Okay, grams to moles. Notice that I am in the same every time. So NH3 to NH3. This week, we've added this step. Moles of NH3 to moles of N2. This is the new step, okay? This is the step that allows us to go from one molecule to something completely different. And then this last step, we could go to grams of N2. And again, these are the same as last week, okay? Last week you converted the same thing every time, so grams to moles or moles to grams. This week I'm just inserting right in the center a ratio that allows you to go from A to B, whatever those two are. It could be a reactant to a product. It could be a reactant to another reactant. It could be a product to another product. It doesn't matter the two that it's asking you about, okay? But it's all about that mole ratio. So this is the new step that you guys learned today. So there's a lot more with stoichiometry and how this works, okay? There's a lot more that we're going to continue on with. But again, let's baby step it. So let's look at the paper that I passed out to you. Let's do a couple of these practice problems together. And again, you guys can get a feel for kind of what this looks like. So if you look at the first equation on there, it says we can compare moles of different substances in the reaction by the mole ratio. So look at the reaction. It's N2 plus 3H2 gives me 2NH3. It's the same equation that's on your notes here on the board. Okay, so you really quickly write out your 6 ratios, because we wrote out the 6 ratios for my example at the beginning of these notes. I want you to write out, there's 3 total, 2 reactants and 1 product, so there's 6 total ratios that you can write with these. Okay, so I'm going to give you a couple seconds to do that. All right, so if you look on the board, these are the 6, again, just comparing 2 at a time. So you can compare nitrogen and hydrogen, you can compare hydrogen and ammonia, and you can compare nitrogen and ammonia. Okay, so those are your 6 ratios as far as this equation goes. So again, you're not always going to have to write out all of the ratios, but it's just trying to initially look at whenever you compare 2 at a time, here's where these numbers are coming from. It's always coming from the balanced equation. Okay, so let's look at number 1. It says how many moles of ammonia are produced from 1 mole of nitrogen? Okay, so again, you don't even have to do much of the math here because you're looking at pretty simple numbers here. So what is your ratio of N2 to NH3? Starting in N2, what's the number in front of N2? 1, and what's the number in front of NH3? 2. So it's a 1 to 2 ratio. So that's asking me if I have 1 mole of N2, how many moles of NH3 do I have? 2. Yeah, 2. When it's 1 to 2. Okay? You can set up the T-chart for that, but I mean, you're more than welcome to. But it's telling you in the equation. It's a 1 to 2. So if you have 1 of N2, you'll have 2 of NH3. Okay? Same thing with number 2. I don't think we really need to set up much of an equation for this. I think it's pretty straightforward. So how many moles of H2 are needed to react with 2 moles of N2? Okay? So again, look at N2 versus H2. It's a 1 to 3 ratio, right? So that means that hydrogen is triple whatever nitrogen is. It's a 1 to 3. So if you have 2 moles of N2, how many moles of H2 do you have? 6. Because it's 1 to 3, which means it would be 2 to 6. What if it was 3? Then what would your number be? 9. It's just triple whatever your nitrogen is. Okay? So again, you can set them up with your T-chart, but like numbers like that, you can just look at them and kind of figure this out. All right, number 3. I want you to set up number 3. You have 5.4 moles of N2, and I'm asking you to go to moles of NH3. All right, so my starting point was 5.4 moles of N2. I set up my T-chart here, moles of N2 on the bottom so that it cancels. Moles of NH3 on top. And where do these numbers come from again? Your equation. What's the number in front of NH3?
2.
What's the number in front of N2? 1. What's 5.4 times 2? 10.8, right? Thank you. You look adorable.
Thank you.
All right, so 10.8. So again, you set it up as I showed you, but NH3, it's a 1-to-2 ratio. So whatever N is, NH3 is literally just double that, okay? All about ratios. How are you guys feeling about mole to mole conversions? See, you can do stoichiometry.
We're stoichiometrists.
You are stoichiometrists.
Whoa.
Yes, you are. All right, so I was going to go a little bit further on this paper, but I'm actually going to stop because I want to give you guys some time. The paper, the descriptive chemistry paper. So you guys are going to work on for the rest of the period about 15 minutes, and you should be able to come pretty close to finishing. You have a paper that's called Descriptive Chemistry and Molar Masses. This is a good review. Remember that now that we're in stoichiometry, it does not mean that everything that we've done up to this point we can forget. This still very much involves reactions and products and being able to predict and kind of know molar masses and all that stuff. So this paper on the front side is asking you, it says some are slow, some are fast. So it's going to explain to you a slow reaction. And it just wants you, in the paragraph, it tells you what the different things that are happening are. So it tells you in the top box, write the names, and then write their formulas with their phases, so either solid, liquid, gas, or aqueous, and then the color description, which it all tells you up in that paragraph, and then it asks you to go through and kind of answer a couple questions. You have 2 things. That's the slow reaction, and on the back side of that is your fast reaction. So again, read the paragraph and be able to kind of pluck out those reactants and those products. You should also be able to know what the products are just by looking at your reactants, because we've done types of reactions before. That should be pretty straightforward. So that part is your homework. The paper that I have attached to it, guys, this is optional if you want to review for your quiz on Wednesday. This paper would be a really good litmus test of how well you know this. This paper is empirical, percent comp, molecular, moles, and hydrates. So you have pretty much everything that your quiz covers on Wednesday on this paper. I have the answers. So if at some point in the next day or two, if you want to check it before you take your quiz on Wednesday, please do that. And it doesn't have to be during this period. If you want to come in and double check your answers during another period, that's fine too. But it's up to you. I would strongly recommend you do at least a couple just to kind of see where you're at. But I'm not checking that one. That one's just for you if you would like. Okay, so again, you have the rest of the period to finish this paper. Whatever you don't finish, you will bring back tomorrow finish, please? And we're going to be doing stoichiometry for a while. So this is just kind of step one. So I promise we'll walk everybody through it.